So theory of the Fick principle before we get into calculations, but we will do some calculations. If you're not the individuals that are not here, but say your peers, your friends aren't here and they come in halfway through the calculations, that's going to make very little sense. The hardest calculation, though, I am saving for next week. The first two, somewhat easy, or maybe not easy, but straightforward. And there'll be a nice warm-up to the calculations that you have to do in lab. All of the calculations are according to the Fick principle, and we use this to measure whole body cardiac output. And it is the same Fick that we've already had some experience with. Adolf Fick, after defining his laws of diffusion, which we've used at the lung successfully to describe the exchange of gas across a membrane, was the first to measure cardiac output in 1870, fairly prolific scientist. Measuring cardiac output in 1870 is one thing. It took him 30 years then to describe the relationship and publish it, which we boil down to, in general terms, delivery of a substance is the flow rate times the concentration of that substance. Which makes sense. If you parse it out, if you think about it, the amount of something that a tissue receives, or the amount of well, let's use like the sink example. Water's usually empty, but if you dissolve something in water, say a dye, the amount of dye, the absolute gram amount that you would see in the sink is how quickly you fill the sink times the concentration of the dye. Just measuring concentration doesn't tell you how much accumulates in the sink. So you need both of those things to figure out the net delivery of a substance. And his equation is a bit more detailed, and we're looking at that detail today, but in overall terms, this is what it describes. So we're going to think about what terms we know already that might satisfy or allow us to figure out delivery, flow, and concentration. I like introducing this idea using a somewhat simplistic example that might be easily relatable. Maybe the sink example doesn't work too well. The animations are slightly out of order, but have you seen sushi conveyor belts? Maybe you haven't been to a sushi conveyor belt or a sushi restaurant where you can just pick the sushi off the conveyor belt as it goes in front of you. But I'm going to use that as an example. As an example to explain or convey the idea of delivery rate. It's not just how quickly the conveyor belt is moving, and it's not just how much sushi is packed into a certain space. It's both of those factors. So if you are at the terminal end of a conveyor belt, the amount of sushi that you see depends on how quickly the conveyor belt is moving. And here I've just chosen 1 meter per minute, which is quite slow. And then the amount of sushi per meter. Let's say you have 3 plates of sushi, or 3 individual sushis, whatever you want. The delivery ends up being 3 plates per minute, which is probably doable, at least at the onset of an all-you-can-eat sushi experience. Later on, it's a little bit more difficult. But this assumes that nothing is left over. So you are at the terminal end of the conveyor belt, and you are tasked with disposing of all of the sushi that you see. That's total delivery. This is to illustrate the concept of delivery in simple, non-physiological terms. So you can imagine 3 of these plates per meter. The conveyor belt is traveling slowly, and you have to scramble to shovel them away. 3 sushis per minute, not too bad. This isn't a physiological example. It's also not necessarily a realistic example, because total delivery doesn't indicate usage. The word delivery could be, it could imply the amount of a substance seen by a target, seen by a tissue, or seen by yourself. But total delivery assumes that everything is disposed of. So I'm going to use net uptake or even net delivery as a term to describe a situation where you don't eat all the sushi. Maybe you're getting full, you can only eat 2 of the 3 sushi plates that you see. Some sushi is still delivered, but not all of it. So how do you figure out what the uptake was, or the delivery to the tissue of interest? The net delivery, the net uptake, is flow rate times the change in concentrations. Overall concentration, 3 sushi per meter. But let's say we don't eat 3 sushis, we only eat 2. We're leaving 1 on the conveyor belt to be sent to someone else. We're being generous. So the net uptake is we have the same rate of delivery or the same flow. Conveyor belt moves at the same speed. We see 3 sushi plates come in. We let 1 go. The net difference is obviously 2. Net uptake is 2 sushis per minute. You can also think of this as extraction. And I'm starting to use words that are going to parallel the physiological situation. If you substitute oxygen for sushi, you're on your way to understanding extraction of oxygen by the muscles of the body. It sees some oxygen, doesn't use all of it, some of it's extracted. If we can figure out the change in concentration and the flow rate, we can calculate net uptake. So a foolish example to illustrate the point. Net uptake or extraction. We're taking the exact same principle and moving into the body. The equation, if we put terms to it, net uptake would be VO2, the net consumption of oxygen. Flow rate would be how quickly the blood that's carrying the oxygen flows. And the change in concentration, you might have seen this term before, is the AVO2 difference, which simply means the difference in arterial and venous contents of oxygen. Arterial has so much, the venous has slightly less, and it's the difference between those 2 compartments that is the change in concentration, or the difference in O2 contents. And this describes what we call the direct Fick equation. Fick equation in words, the direct Fick in symbols is listed above the words. You could plug numbers in to these terms and calculate one of the missing terms. And we're going to try to do that for cardiac output because we don't have numbers for that yet. But we've seen VO2 a lot of times. We know how to get that. Maybe there's a way we can get the AVO2 difference and calculate cardiac output. I'm going to introduce the idea here as well, and I'll return to it as we build some examples going forward. This can be at any level. So if you're measuring VO2 at the mouth, at the whole body level, and then you have whole body arterial O2, whole body venous O2, you can figure out whole body flow. Compared to, if you did this at, let's say, quadriceps, if you could calculate the oxygen consumption of that muscle, the flow in that vascular bed, and the arterial venous difference across that capillary bed, you could calculate VO2 of the quadriceps themselves. It all depends at what level you obtain the data for this equation. Whole body or at a tissue-specific level, anywhere in the body, but you can translate this equation accordingly. So what's the significance of doing this? We've alluded to this already, but we have some foundational equations of physiology. And we can fairly easily, depending on how practiced you are with the blood pressure cuff, measure mean arterial pressure. It's really easy to measure heart rate if you can count and keep time, or if you're wearing a heart rate monitor. But it's difficult to measure total peripheral resistance, which we talked about yesterday is a dimensionless term with many ingredients, and we don't really care about the ingredients as much as what's the global resistance, or what's the resistance to flow. It's hard to measure that, and it's equally difficult to measure stroke volume without some more expensive, invasive equipment, or for our purposes, it's hard to measure it. But because these equations hold up, and it's easy to measure the two in blue, if we can ever figure out cardiac output, then we can calculate stroke volume. We can calculate resistance. And I'm just assuming that you want to make that calculation. Maybe you're going to argue that it doesn't matter. But it would be pretty cool to know what the total resistance to flow is, and if not that, what stroke volume is. That's pretty interesting. So let's put this example into practice. And in general terms first, let's think of a scenario. We're looking at some compartment, some area in the blood. The white dots are oxygen, and let's say we have a hypothetical scenario where delivery is 5 oxygens per minute. We have a certain rate of flow, we have a certain concentration, and then delivery, I'm freezing the oxygen molecules in time, is 5 per minute. And to illustrate the equation, if this sped up, in scenario 2, we change only one thing. Let's say flow rate speeds up, same concentration, but because of the faster flow rate, we don't know what the value is, but delivery should be more than it was in scenario 1. Flow's faster, delivery should be higher. And that should be no surprise. And the opposite would be true as well. If flow slowed down, delivery would be lower. So this is to get a sense of how the equation works in the body. And now we're going to look at how we might calculate or apply this. Let's start with the tissue. Let's start with the muscle, because this is the unit that uses oxygen. So the muscle is subject to substrates, oxygen, anything that's being delivered to it in the blood. And here you can see blood flowing by, oxygen in that blood, and some of it's being extracted. One of those oxygens is meandering out into the muscle. And this always happens. Metabolism in the muscle dictates that we need to consume some oxygen. And let's say, for argument's sake, that instead of oxygens per minute, each one of these dots now is 100 mils of oxygen, to put it in physiological terms. Well, we've got 5, and I guess you can't really see the 5, but there are 5 coming in from the arterial blood, so 500 mils of oxygen per liter. And if one of those, if 100 mils is diverted to the muscle, we're left with 400 mils of oxygen per liter in the venous circulation. And I'm going to say arbitrarily that the speed of these dots moving through this compartment is happening at 1 liter per minute. So you can even intuit there's a difference here of 100 mils of oxygen. If that happens once every minute, the muscle's taking out 100 mils of oxygen in every minute. You can put the numbers into the equation, but you can use logic and figure it out. It makes sense. We're extracting 100 mils of oxygen per liter of blood, and that blood is moving at 1 liter per minute. So if we simplify, we're extracting 100 mils of oxygen per minute at this tissue. All we've done in describing this verbally is apply these nice, easy, round numbers to the direct Fick equation. We've taken 1 liter per minute, that's our flow. The arterial O2 was 500 mils of O2 per liter. The venous O2 was 400 mils of O2 per liter. The difference then is 100. 100 times 1 liter per minute gave us VO2 of this muscle. Pretty straightforward, right? Is any of this not making sense? Because we're going to build on these examples. And if you're being left in the dust now, it's going to get more complicated. Good? Okay. We don't care so much about the muscle. We care about the whole body. If we can do the same process, but at the whole body level, then we can calculate whole body flow. VO2 at the whole body level, easy to measure. We have metabolic carts that can do that. In a pinch, we can calculate it ourselves. If we can measure arterial and venous O2, then we can do the same exact thing that we did on the last slide. Satisfy the equation. I guess it's not the exact same thing because the unknown is different in this case. The unknown is flow, whereas on the last slide, the unknown was uptake, or net uptake. It's still plugging numbers into the equation and solving. So let's see, the focus of this lab is to calculate Q, or cardiac output. Let's imagine where we would get this information. If we get that information, we can plug it right in. So I'm going to help us out by expanding the term a little bit. Instead of AVO2 difference, I'm going to write out arterial O2 minus venous O2. So those are two separate terms. We want to find each of them. We want to find VO2 and then calculate cardiac output. And it's dead easy to start with VO2 at the whole body level. Metabolic cart does that for us. We can calculate it, and I'm not going to show you how here, but when we get to CO2, there's an example of how to calculate whole body consumption or production in that case. We'll leave that for later. We're going to assume that we have that at the whole body level. Where do we get arterial O2 concentration or contents? In the arteries. Which one? Okay, if we're doing it at the whole body level though, whatever one's the easiest to access. Any artery. All the arteries have oxygenated blood, they've been mixed at the heart, same concentration of substrates, same content of oxygen. There hasn't yet been the chance for any active tissue to remove substrates and oxygen. Any artery. All arterial blood is uniform. But arterial blood is contained within the arteries. Arterial blood is hard to sample. High pressures, Push the plunger of the syringe out. Generally difficult to recover from. Lots of pressure. You don't want to leave an open wound on an artery. You bleed out. Difficult to measure. Let's say that we had the technological expertise to do that. Where do we have venous O2? This one's trickier. Veins. Can you use any vein like we used any artery? No, that's the correct answer. Why not?
Because it's close to the exercising muscle, then it's different substrate.
Okay, so if you measure at a vein just downstream of a very active muscle, then it looks like a lot of oxygen has been extracted. What if you do it at a non-metabolically active tissue, or not highly metabolically active? What does that O2 look like? The opposite, so you have a lot left over. If we want to measure at the whole body level, we want representative venous blood. What do I mean by representative? Average. Average of what?
All the different concentrations, like
Yeah.
where it is taken out a lot and where there's not a lot.
Average of all the tissues. Average of the metabolically active tissues or the lesser metabolically active tissues. Mixed venous blood is what we're talking about. And where's the only place that we get mixed venous blood?
Right ventricle.
Right ventricle, yeah. Right ventricle, right atrium, right side of the heart. All the blood returns through the vena cava, and that's the last point where you have two divergent samples, right? All the blood from the rest of the body ends up at two large veins that combine together, and it's that combined sample that we want to measure. So if you thought measuring arterial oxygen was difficult, this is 100 times more difficult and invasive. This is like the stents. This is inserting a catheter in a distal vein, snaking it all the way back up through the subclavian vein, superior vena cava, into the heart. You would put it into the atrium of the heart. So through the valves into the atrium. Can't really do that in a student lab. Hard to do that in a research lab without proper expertise. So the direct Fick works. You can calculate cardiac output if you have the appropriate information, but it's invasive. It's hard to get that information. And so we're not going to use it. You could, but for these reasons, it's very difficult to collect the proper data and then use it accordingly. So, is there anything else in the blood that mimics the path of O2? Maybe not the exact path, but is subject to net delivery, subject to flow, and subject to differences in concentration across the heart. Something that at the whole body level that we can, you got an idea?
CO2?
Exactly, CO2. CO2 is the evil twin in this case, why the balls are all black now. CO2 isn't extracted from the blood, it's added to the blood. But it's carried in the same bloodstream, so at the same rate. We should be able to calculate the net, not uptake in this case, but the net contribution or the deposition of CO2 in the arterial and the venous circulation. And we can use the Fick equation in reverse. Let's imagine what that looks like. So now, instead of oxygen traveling in the circulation, we have CO2. There is some CO2 in the arterial blood. The muscle, in this case, is contributing new CO2 because it's a byproduct of metabolism, so that there's more in the venous blood. And that should agree with your current understanding of physiology. That makes sense. Well, let's say 500 mils, each one of these dots still is 100 mils of a gas per liter of blood. This is now 500 mils of CO2 per liter of blood. There's 5 on the arterial side just to keep the numbers consistent. If the muscle is adding one bolus, 100 mils of CO2 per liter of blood, then on the venous side we have 600. If flow rate is the same person, same situation as our first example, then now this muscle is depositing 100 mils of CO2 per liter of blood at 1 liter per minute. Overall, the net deposition is 100 mils of CO2 per minute, or the VCO2 is 100 mils per minute at this specific tissue. It should be familiar. It should seem like we're in the twilight zone, talking about the same exact things. We are simply tailoring the Fick equation to CO2. Whereas before, our focus was oxygen. Now, we're using CO2. It's still a substrate in the blood, limited by the same constraints of diffusion across a membrane. VCO2 is flow times the difference in arterial and venous CO2 concentrations. This is what we refer to affectionately as the indirect Fick. It's still the Fick equation. It's not as he originally intended it, with oxygen as the operative term. Now we're using CO2, so in an indirect manner we're calculating cardiac output. If we can do this at a tissue, we can do it at the whole body. In the same way that VO2 is easily measured at the whole body, we can measure VCO2. It's an often overlooked column on the printouts of the metabolic cart. VCO2 is measured at the whole body level, easily. Is it ever possible now to measure venous and arterial CO2 contents? It was possible to measure O2 contents, but invasive, involved, difficult. Is it equally invasive to measure CO2 contents? Now you will notice that I've swapped the order, the venous and arterial. The order is in reverse in the indirect equation, simply because the direction of flow of the gas is opposite. And so I've changed the order to keep the number positive, essentially. So we don't have to work with negative numbers. You could keep it in the same order as the direct Fick equation, and then the negative symbol would just tell you the direction is opposite to that of oxygen. But why go through that unnecessary added complication? We're just going to keep the numbers positive, so I've swapped the two numbers to keep the value positive. And in the same way that I separated those two values before, I'll do that here, and we'll explore where we get each number from. So again, VCO2 is easy. At the whole body level, we get it from the metabolic cart. The others are not so easy, and I'm going to throw up this little schematic that really should give us arterial and venous CO2 contents. Venous CO2 is the highest, and here it is incoming to the lung. This is whole body mixed CO2, if we can ever sample that. And then leaving the lung, we'd have whole body arterial CO2 after full equilibration, right? So if we could measure across the capillary in the blood, we could get CO2 contents through a direct measurement. But we're not doing that. Blood samples through capillaries, pretty invasive. Now we want to explore if there's ever a way that we can make blood measurements in an indirect manner through the lung. And I suppose that's really where the term indirect comes from. We are measuring blood contents through a gaseous sample, through a lung sample. That's really where the indirect comes from. So let's start with the arterial CO2. That's actually the easiest. And if you're following along on the slide set online, by the way, a few of the points have changed. I've tweaked a couple of the descriptors, and some of the numbers are even a little bit different just to make them flow a bit more easily. So just be aware of that if they don't agree immediately. The slides that I'm showing you up here are probably better and more descriptive. So where do we get arterial CO2 from? We want to measure CO2 contents in this blood. Where can we get an approximate estimation of that using a lung sample? What assumptions would allow us to use an air sample at the lung to approximate blood CO2? Give it a shot.
How much you inhaled, and then how much comes back out in the next breath?
How much you inhaled and how much comes back out. Okay. That is a lot of info, and you don't actually need how much comes in, but you do need how much goes out.
How come you don't need how much
What?
goes in?
Sorry?
How come you don't need how much goes in? Because wouldn't you need to be able to see the difference?
We are getting the difference from the venous CO2 measurement. The arterial, we just want to know how much is leaving the capillaries. We want to know the value here and how that value is represented in the lungs. So the value in the arterial circulation doesn't really have a bearing on the CO2 inhaled. And for that matter, what is the amount of CO2 you would inhale? If you were to round it to the nearest tenth or hundredth of a percent, what would it be? How small?
Is that like 0.3% or something?
0.03%. So the fractional number is 0.0003 mils of CO2 per liter of air. You'd round that to 0. So essentially we are doing what you're saying, but the incoming CO2 is incredibly small, so as to not affect the measure. But what happens at the lung as gas travels through the blood in the capillaries, in contact with the alveoli? What should happen as CO2 leaves the arteries? How is that reflected in the air in the alveoli? Aaron?
Do you assume that when CO2 is transferred into the alveoli, it'll come to a point where there be an equilibrium in the blood and in the alveoli, so it should be the same concentration?
Yes, that's exactly right. We are assuming the alveoli and the lungs in general do their job of allowing gas exchange. We are assuming that it is full gas exchange, which means they enter into equilibrium. As CO2 travels through the capillary across the alveoli, the amount of CO2 in the arterial blood leaving should be reflected in the CO2 in the alveoli if we have full equilibration and if there's equilibrium. Well, let's follow the CO2 in the alveoli. If that reflects arterial CO2 and we can measure it, then we should be able to get some sense of what arterial CO2 is. The air that travels out of these alveoli, if nothing happens to it, should have the same CO2 concentration as arterial CO2. So we just want to follow the air out until we get to a point where we can measure it easily, make that measurement, and that should allow us or be representative of arterial CO2. Air out of the lungs is approximately or has approximately the same partial pressure as the arterial CO2 leaving the capillary. And we know that to be approximately 40 millimeters of mercury. If we measure it in the air coming out of the lungs, it should be about 40 millimeters of mercury, and those should match because we have full equilibration. In the lab manual and throughout the rest of the talk, I'm referring to this as end tidal CO2. And that simply means at the end of a tidal breath, after you expel air from the lungs before breathing back in again, whatever that value is at the end of your breath is most likely representative of arterial CO2 partial pressures. And we'll talk a bit more about the mechanics as we go through the calculations. But if we have full equilibration, air in the alveoli should mimic air in the arterial circulation. If we can measure that air, we should be able to calculate or estimate arterial CO2. Pretty straightforward. How do we get venous CO2? That's not straightforward. Yeah.
Would it be if you added the two together? Because you got the concentration in the arteries and the concentration that went into the alveoli, like if you doubled it?
If you doubled it.
You're assuming that the alveoli is starting at 0.
Right. If we assume the alveoli starts at 0. Okay, I see the logic in that. And then you would double it, assuming that you went from 0 to whatever the partial pressure is, and then that represents half of the sample that would have come in. That's actually a pretty smart way to do it. The only problem is the alveoli don't start at 0. If they did, that would probably hold up. But they don't start at 0. And so there's no way to know if you measure a change or an increase in PCO2 if that represents a third of the incoming or half of the incoming or a fifth of the incoming CO2. There's no way to know. But that's an interesting approach. Essentially what I'm asking is, how do we cut out gas exchange, right? As soon as the CO2 in the venous blood is in contact with the alveoli, gas starts moving. And to get the arterial sample, we want that to happen. We want full movement, which is good because that's the job of the lungs, and that happens, it proceeds on its own without intervention from us. But now, we don't want gas exchange to occur. We want to measure this before it even comes into contact with the alveoli, essentially. Even if you wait until the point where CO2 is in contact, some of it slipped out of the venous blood. How would you ever stop gas exchange from occurring?
You change the concentration gradient. So
Okay.
the gradient was imbalanced.
How do you change the concentration gradient so the gradient is balanced? That's exactly what we're doing.
So you have to breathe in enough CO2 so that
Okay.
wouldn't exchange across.
Yes.
So that whatever CO2 you breathed in was the exact same that you would breathe out.
Okay, that's actually a second variation on the rebreathe technique. So there are two types of rebreathe. One is the exponential, which is what we're doing, and the other one is the equilibrium, where you prime the lungs with some CO2, which is what you're describing. They both achieve the goal of stopping diffusion. We don't have the equipment that can meter out gas with enough CO2 in it at the appropriate level to breathe in to match venous CO2. We don't have that technology. So we're going back to basics. We're doing the exponential technique, but it's the same approach.
Is the problem to calculate the right amount?
Yeah,
Yeah.
for the second example, it's usually always automated, and the metabolic cart will be able to measure breath by breath CO2, and then it fills a bag before you start the measurement with CO2 filled gas. That's meant to approximate the lungs, and then when you breathe that in, it should just clamp diffusion from occurring. We don't have the ability or the technology to do that calculation and fill the bag beforehand. It's too advanced for the equipment that we have. I'll give you the answer quickly because you're on the right track. We want to stop diffusion. Instead of giving more CO2 to match the incoming CO2, if we simply block gas exchange, then CO2 will accumulate in the alveoli, eventually reaching a point where it is equalized across the capillary, eventually reaching a point where there is no exchange of CO2. So if we block the diffusion out of CO2 and we start to collect it in the lungs, it will creep up, it will increase, it'll gradually slow down as the gradient gets smaller and smaller and smaller to the point where it's in equilibrium. The CO2 in the lungs matches the CO2 in the veins. If there's no gradient, there's no movement, and if we can measure at that point the CO2 contents of the air in the lungs, then we can approximate the CO2 content in the veins. Yeah, Razan.
So how would you block, per se? Like, do you hold your breath, or?
I will tell you exactly that in 1 second. And it's also, it is the point of the lab. It's in the lab manual as well. Let me just make sure this point is clear, and then I'll get to that, the answer to that question. So does it make sense? CO2 gradually accumulates in the alveoli. Eventually it'll slow down and reach equilibrium. And then that point of equilibrium is where the CO2 in the air equals CO2 in the blood, and if we can measure one, we can get or calculate the other. Does that make sense? Now the question is, how would we ever do that? Razan's question is, how do we ever do that? We do block the lungs. In lab, we will be doing that this week, today. We don't block the alveoli. We don't have access to the alveoli. We only have access to the mouth. You block all gas exchange by rebreathing into and out of a bag. So a sealed bag. Like when your parents said don't put a plastic bag over your head when you were a kid because you'll suffocate, we're doing that in a controlled manner. It is the same thing. If you did it for too long, you would die. But you're not doing it for too long. So there's some very quick and precise movements that you have to do, and you change the direction of flow. We have valves set up. You're breathing through the flow sensor normally, and then when you start the rebreathe process, the subject takes a breath in, you change a valve so that instead of breathing into the air, they breathe into this sealed black bag, rubberized black bag. Bag fills, and then as they take their next breath, it doesn't come from the air, it comes from the bag. Into the bag, out of the bag, into the bag, out of the bag. All that does is ensure that, okay, well, we're trying to diffuse CO2 out. Normally it would go to the environment, be dissipated, and we'd bring very low CO2 back in, but instead now it goes into a bag where it collects. We bring a higher CO2 back in. We add more at the alveoli. That higher concentration goes into the bag. That goes back into the lungs, and we achieve the goal of reaching that equilibrium. So if we can see that equilibrium happen in that lung bag system, then we can calculate venous CO2. That sounds a lot nicer than putting a catheter into my right atrium, personally. There are a few caveats with this. Number one, this assumes that we have no recirculation. In other words, it assumes that we reach a point of equilibrium. But there's a problem. We can close off the lungs to collect CO2, but we can never stop the input of CO2 from the body. Muscles, active tissues, always producing CO2 as part of normal metabolism. So even if you clamped off the lungs and you did the rebreathe for a minute, you would never actually reach equilibrium because you're always adding CO2 on the venous side. So we don't ever get to measure the point of equilibrium. What we measure is how the accumulation levels off. As you close the lung bag system, CO2 will start to accumulate quickly, and then the accumulation will slow as it approaches equilibrium. We're measuring the rate of slowing. And I'll show you why that's important when we get through the calculations. But it assumes no recirculation. Big benefits are that it's not invasive. So we can do this. We can get all of the values to satisfy this equation. We can get VCO2. We can get arterial CO2 by measuring just air at the end of each breath. And we can get venous CO2 by trying to approximate the point of equilibrium when we close off the lungs. If we have those three values, we can calculate cardiac output. I also just want to take a minute, we couldn't do this in the middle of the explanation, to show you the diffusion of CO2 across the lungs. We've seen something like this for oxygen. We were talking about transit time and compromised gas exchange. This is CO2 out of the blood into the alveoli. CO2 starts at maybe 50 millimeters of mercury. In the alveoli, it's 40, and it's near instantaneous. There's never a question when you're trying to measure the end tidal CO2 that it hasn't equilibrated with the arterial CO2. It does it right away in 0.05 or 0.1 seconds. So this shows that the flat portion should be the air that we breathe out with every breath. There's a high likelihood that this has fully equilibrated. Now this is the theory of the rebreathe technique. From this point, most of you will move into doing labs this week. With this background knowledge, you would read the lab manual, go in, execute, get the experience of performing the rebreathe technique. You would collect the three variables of interest, the three data points of interest: VCO2, arterial CO2, venous CO2. Not all of you will get to do that this week. And so as we go through the second half of the calculations on Tuesday, some of you won't have that experience, but I'm going to try to level the playing field a bit by taking you through some calculations with no experience and set the stage for how you do the calculations moving forward. So now we are assuming that you've been to lab and collected this data. You don't have the intimate knowledge of how the collection was done. We are assuming that you've collected numbers for these three terms: VCO2, venous, and arterial CO2 contents. Yep.
Reason that we started with VCO2 instead of VO2?
Yes, there's a reason that we're starting with VCO2 instead of VO2, because if you want to use VO2, you need the arterial venous O2 difference. And we just spent a little bit of time talking about how that's hard to assess. So we're throwing VCO2 out. It's still good information. We can use it to figure out when we're at steady state. But as far as using that number in a calculation, it's not applicable. Yeah. So imagine that you've completed lab 4. You've done the rebreathe technique. You've breathed into and out of the bag. Now what? And for any of you that end up doing the rebreathe, it's a pretty cool experience. It's really hard to describe unless you do it. The knowing that CO2 is the prime mover for ventilation, you get into a situation very quickly where you start to look around and the alarm bells start to sound and you start to breathe a bit heavier because you're accumulating CO2. I suppose a brief note about how to do this properly. We want to avoid any circulation, and you want to make sure the subject, the participant, is healthy and comfortable. None of your collection should last longer than 20, 30 seconds, maybe 30 seconds at rest. In exercise, maybe 7 to 15 seconds. It won't be long. You'll need to be well practiced with changing the flow and making sure that they're okay. And if you are the person doing the rebreathe, try to go as long as you can. You might start to even see like a few stars or specks. Of course, if you have to, just take the mouthpiece out. Just ditch the mouthpiece if it becomes too much. But breathing in and out into a bag, it's not a comfortable experience. And CO2 has a very odd metallic taste. So sitting here, think of what it feels like to breathe. The air's kind of fresh, it's cooler, it's clean, for lack of a better word. During the procedure, you're breathing moist air, it's warm, and it's metallic. And the alarm bells are going off saying something's wrong. So it's not a comfortable process. It's a really unique experience, though. Let's say that we've done it correctly. You have data for the right time frame. There's no recirculation. We have steady state information leading up to the rebreathe, and that's an important point to bring out in the lab too. You should be well practiced, I think, at this point. If you're doing stages, you wait until you get to the steady state for that stage. VCO2 numbers come from steady state. You want to know at rest or at that intensity, what's a typical VCO2? The arterial CO2 number also comes from steady state. You want to know what's the typical CO2 contents at the end of a normal breath. The only data that comes from the rebreathe is the venous CO2 content. And I do bring that up again later, but we're on a roll right now. So imagine that you've gone through this uncomfortable procedure, and we'll start with VCO2. You have this number. I'm going to show you, for argument's sake, if you don't have the number or the calculation is not done for you, how you can get VCO2. But you will get average VCO2 over 3 20-second bins from the Metcart printout. VCO2. And I'm showing, this is the indirect Fick that's going to follow us along in the top right of every slide, just so you can refer back to it. But if we needed to calculate VCO2, you would do it as follows. VCO2 is ventilation times the difference. This is the fraction of expired CO2, FeCO2, and the fraction of inspired CO2, FiCO2. And I should be a subscript. It's not here, but the fraction of expired CO2, the fraction of inspired CO2. And fraction of a gas is resolving the percent. right? So you think of a percent of gas, oxygen's about 21%, CO2 is about 0.03%. And when you say percent, it's literally, for oxygen, 21 divided by 100. That is when you say percent, literally that's what you mean. Percent, per 100. So fraction of a gas is resolve that fraction, resolve that percent. So it's the decimal form of the fraction. 0.21 for oxygen, 0.0003 for CO2. That's what I mean by fraction of inspired or fraction of expired CO2. Does that look familiar? No?
Similar. Looks
How?
similar to the indirect.
How? Why?
You have a flow rate, and you have a difference concentration.
And what else do you have?
Delivery.
No. This is the Fick equation. This is the Fick equation coming from the environment looking at the body. It's the same exact equation. The net production of CO2, the flow rate of air, and the difference in CO2 contents. We're looking at it from the point of view of the lung now, looking inwards. It's the Fick equation. It's the same exact thing that we've done all this class. And if you had numbers for ventilation and the fraction of O2, or the fraction of inspired and expired CO2, you could put them into the Fick equation and calculate VCO2. So I'm arbitrarily choosing, let's say, resting values. 8 liters per minute or 8,000 mils per minute of ventilation. And I'm purposefully doing this because I want to keep the units consistent throughout, mils of air per minute. And I'll show you why in a second. Times the fractions of the gas. I'm going to hold off on giving you the expired CO2 for now, but we've already talked about how CO2 in room air is very, very low, 0.03%. or 0.0003 fraction of inspired CO2. Well, VCO2 then is 8,000 mils per minute times the difference between those two, and let's say a representative expired CO2 is 5.6%. Usually about 4 or 5% of the air that you breathe out is CO2. So I'm just making that number up. This is something that you might see on the metabolic cart when you look at end tidal CO2 or fraction of expired CO2. So that fraction, 0.056, I'm literally going to just figure out the difference and multiply by 8,000. So my VCO2 is 440 milliliters of CO2 per minute. So it's important, I think, for the ease of continuity in these examples, milliliters of CO2 is something that carries through the calculation. That's why I started with 8,000 mils, so that we end up with mils of CO2 per minute down here. That number we will use in calculations that are forthcoming to help keep our units consistent. You could do 0.44 liters per minute if you wanted to, and then just adjust the units later, but for ease of uptake. And that's it for VCO2. And you don't even have to do that calculation. You get that from the metabolic cart. You see the average 440 mils per minute over 20 seconds or over 30 seconds or over a minute. You get steady state VO2 from the met cart. One down. And that's as easy as it gets. So what do we need next? We're going to go to arterial CO2 next, and then venous CO2 on Tuesday next week. We should have enough time to get through arterial CO2. Arterial CO2, by the theory that we've established, should be CO2 that's expelled with every breath, or end tidal CO2. This is end tidal CO2 as a percent. I think technically this is partial pressure of the end tidal CO2. PET CO2 should be millimeters of mercury. You will see both on the Metcart printout. I'm going to go through how you get from point A to point B, starting with percent, which is the minimum amount of information that you need. You end up converting to millimeters of mercury, and then you go to contents. That will become clear. But you get this information also from steady state. Both of those are from steady state, representative values for whatever the stage is. And so looking forward, the end tidal CO2 number during the rebreathe portion, or the point of equilibrium that we're trying to approximate in the rebreathe, comes from not steady state. This is from the rebreathe maneuver itself. In either case, you're going to get numbers in percents or in partial pressures, but pressures aren't contents. And so you need to figure out if there's a pressure indicated here, what does that indicate is the amount of CO2 in the blood. We don't want pressure, we want a volume of gas in the blood. We want contents. And whenever I say contents, I mean mils of CO2 per liter of blood. It's concentration, essentially. Pressure is not contents. The standard term, or the standard units for contents, are mils of CO2 per liter of blood. Sometimes it's mils of CO2 per 100 mils of blood, but I'm using these units, again, to keep consistent through the calculation. Mils of CO2, why we calculated VCO2 as we did. Before we get into numbers and an example, I want to show you how we correct pressures to contents. Pressures to contents. So when you get the data from the metabolic cart, you might get a percent. The first step in finding contents is to figure out the partial pressure from that percent. And we've done this already, right? Remember, atmospheric pressure has some total pressure, and then the percentages of gas in that atmosphere contributes to atmospheric pressure. So 21% of 700 millimeters of mercury is pressure due to oxygen. 0.03% is pressure due to CO2. The rest is pressure due to nitrogen. So we're just doing that calculation again. We have atmospheric pressure corrected for water vapor pressure. And if we have percent of CO2 in our sample, we are just figuring out, okay, well, that percent of the total atmosphere gives me what partial pressure? We've done that calculation before. This isn't anything new. It shouldn't be difficult. And we do that because we don't have a way to relate percent and contents, but we do have a way to relate partial pressure and contents. And I'd like to tell you that there was a magical, logical explanation for it. It just simply follows this relationship. They are fixed depending on the gas, where for any given partial pressure, it represents a certain content in blood. It also changes for different fluids. This is for blood specifically. So we see comparative traces. There's one for oxygen along the bottom, but we don't care about oxygen because we're not using that in our calculations. We care about CO2. We're going to get a partial pressure of CO2, and we want to follow that up to its point of intersection with this curve, and then figure out where that is on the y-axis contents scale. For every partial pressure, there is a contents, and it adheres to this equation. This is a fixed equation. You just put in the PCO2, the partial pressure of CO2. If you calculate it out, you get mils of CO2 per 100 mils of blood. This will be static as a conversion. It's like converting kilometers to miles. After you've done this, contents is what we want to put in the equation. So let's go through a quick example of how this might look, and then we'll call it for the day. I know call it for the day sounds like a bonus, but we're almost at the end of class. So let's figure out what this would look like in your longhand calculations after doing the lab. So I'm picking up similar numbers from our first example. End tidal CO2, 5.6%. That's what we used as the fraction of expired CO2 in the VCO2 calculation. Same number, same example, same person. The first thing I want to do is get out of percent. I can't use percent. I need partial pressure. So I turn to my partial pressure equation. The partial pressure of CO2 is the percent of atmospheric pressure. In this case, it's 5.6% of the atmospheric pressure, corrected for water vapor pressure. If I simplify this further, 0.056 times the difference, or the atmospheric pressure corrected for water vapor, 0.056 times 7 to the 13 gives me 39.93 millimeters of mercury. Essentially what that's saying is 39.93 is 5.6% of the atmosphere. Awesome. I've taken an unusable value, not unusable, but one that I can't directly input into the equation, and converted it into a form that can be input into the equation. 39.93 millimeters of mercury in the end tidal expired gas. Remember, this should reflect arterial CO2 because we have full equilibration. Right? 39.93 is the height of this horizontal line. I'm reading that in the expired gas. This assumes full equilibration at the lungs, and arterial CO2 represented here as well. Okay, that makes sense, right? This is what would go out to the rest of the body if we revisit our oxygen cascade. Instead of focusing on oxygen in this case, looking at CO2, yeah, there's full equilibration. Approximately 40 millimeters of mercury in the alveoli, approximately 40 in the arterial circulation, more than that on the venous incoming. But this should be end tidal CO2. But it's not. Wild card. At this point, I need to throw a monkey wrench into our plans. End tidal CO2 is not exactly arterial CO2. There is still full equilibration. Alveolar CO2 is arterial CO2, but something happens to that sample as we breathe it out of the lungs. What happens to that sample? Mixes with the dead space. It travels along its concentration gradient to a point where, hey, there's no CO2 in the environment. So it's lower than it should be when we measure it at the mouth. We need to correct for the fact that it's lower at the mouth than it is at the alveoli, and we can. You can sort of think of this as contamination. Perhaps a better way to put it is dilution of the sample, or mixing with the anatomical dead space. But if you consider the lungs as a system, and all the way down here where the circle is at the alveoli is where we're ideally making our measure. If we could do that, everything that we've done so far would hold up, but that air has to travel all the way out through the trachea to the point of measurement. We're measuring way up here off the diagram. And in its transit through the dead space, it mixes with dilute air, or diluted CO2. It's contaminated, and so it's lower than it should be. But luckily, the amount of dilution is predictable. There's more or less a linear relationship, or we're assuming a linear relationship, between end tidal and alveolar CO2. And really that means between end tidal and arterial CO2. That linear relationship is shown here. Y equals mx plus b. And it's not as clean as that. Actually, there are 3 terms, so maybe strike that. I'll edit that out of the video. But there are 3 terms, but it's an easy correction to get from end tidal to arterial CO2. Some of these subscripts are confusing, and they are done in error. End tidal PET CO2, the E and the T should be subscript. The CO should be not subscript. The 2 should be subscript, but I think you know what I'm looking for here. The measurement that we just calculated on the last slide, in the last example. We input that directly, and then there's a small correction for the size of the tidal breath. This is tidal volume, VT. The T should be subscript, in keeping with convention. Depending on the size of the breath, that tells us how much dilution might occur as that air travels out of the lungs. So we need to correct for the size of the breath. But overall, if we have our end tidal measurement and we have tidal volume measurements, we can approximate, we can correct to arterial CO2. Small detour. And I'll go through this, it'll be quick. I will put it back up in class on Tuesday to take it back up again because maybe it won't be immediately clear. But after that detour, clear sailing. So let's pick up. We have this end tidal CO2 partial pressure that we just calculated, but it's not representative of arterial. So let's make it arterial. This is the equation that I just showed you that corrects end tidal to arterial. And here all the subscripts are correct. Excellent. So I'm going to plug numbers in directly. 39.93 is taken from the example. 0.5 is arbitrary. I made that up. 500 mils for tidal volume is pretty standard at rest. This example, again, is at rest. So I just pulled that out arbitrarily. Now I'm going to simplify. Let's multiply 39.93 times 0.9, and we'll multiply the tidal volume terms on the right. Punch that into a calculator. Maybe you're setting up an Excel sheet to do all these calculations automatically. Who knows? Now I have three things to add together. Hey, they add together 41.44 millimeters of mercury. That makes a lot of sense, right? End tidal CO2 should be lower than arterial. 39.93 is lower than 41.44. The dilution is pretty small. It's not a major contributor, but we want to make precise measurements, and so we do this correction to make sure that our measurements are precise. That makes sense. If this number were lower than 39.33, something went wrong, right? You shouldn't gain CO2 as the air leaves the lung. I'm going to stop. The next thing that we have to do after partial pressure is get contents. One equation to get contents, which is shown here. I'll go through that calculation when we come back on Tuesday. Show you mils per 100 mils of blood, and then we'll go into the venous CO2. But one question before we go? Yeah.
Right, you said that as CO2 leaves the lungs, that you shouldn't get more CO2?
Yes.
Do you mean into the body or into your
No.
circulation?
You shouldn't accumulate CO2 between the alveoli and the point of measurement at the mouth. Yeah, end tidal should not be higher than alveolar. Okay. Lots of numbers for the morning. I get it. But hopefully it made some sense. And see you Tuesday morning to continue our discussion.